So welcome to Math 4. This is Math 4, right?
I hope so.
Yeah, okay, that's what I'm here for. So this is our web page on EEE. If you're not a student here, then you don't know what EEE is maybe. Anybody in that situation? Okay, so most of you understand what EEE is. So this is where you go get most of the information for the course. The most important thing is homework and stuff like that is posted there. Okay, so I'm Jason Kronewetter. That's me. This is my office in Roland Hall, so it's over across the park. And then those are my office hours are right before class, so if you want to come and ask questions before class, then we'll walk over here. Okay, so in case you didn't notice, we're going to film this course. It's not just today, it's the whole course. And so if you don't want to be on film, you don't want to sit down the center row. Okay. So if you want to get here early and sit on the sides, then you won't be included in the film. We're going to post this as an open course, open source course for the whole world for free after we're done filming it. So that's the reason for the cameras. All right. So let's get into what's going to happen in this course. We've got 6 weeks. We have kind of an intimate setting here. It's if everybody shows up all the time, it's going to be kind of packed. But it's a small classroom, so you'll be able to hear me and see the board and everything like that. So that'll be good. Let's talk about grading first. Let's just get all that out of the way. That's the most important thing, right? That's what you want to know. How are things graded, and what are you going to have to do for the course? So a couple things. Here's all the homework for the whole course, and this isn't going to be collected. Homework is not part of the the grading. It's just suggested. Okay, and let's go to the syllabus here. There's a syllabus posted on the web page. Okay, is my TA here? Okay, that's okay. He'll come after class. So there's discussion right after class. And that's where you'll have your quizzes and things like that, and then ask questions about the homework or lecture questions, and then he'll also lecture himself. We'll have a midterm and we'll have a final, and then here's the schedule. So this is just a tentative schedule. If I don't get to everything in one day, then I'll pick up where I left off, and if I get a little ahead, then that's okay too. So this is just kind of a tentative schedule for the summer. So we've got these 2-hour classes. Since we're filming, I'm not going to do a break in the middle, but I'm also probably not going to take the whole time. So we'll just go, it'll be, you can kind of count on it having a little break before discussion, because I'll end a little early. But you can plan on the classes being at least an hour and a half. If I get through all the material I need to for the day, then I'll just stop and let you guys have a little break. And sometimes I'll need to go the whole period because I need to get through something and I don't want to leave off in the middle. So I'll be a little flexible on that. Okay, so there's only 3 things that you're going to be graded on: quizzes, a midterm, and a final. So that's sort of good news and bad news. The good news is there aren't that many things that you're graded on, but the bad news is that if you mess up on any one of those things, you don't have a whole lot of room to make up for that. So you want to take the quizzes seriously. Those should be really easy. You should be able to get good grades on all the quizzes. That's the design anyway. The midterm will be a little more challenging, and the final too. So you want to try to get your points in the quizzes, and then, of course, you're going to try to do as good as you can on the midterm and final. Yes?
Is there going to be a quiz every discussion?
No, it's on the schedule here. So the first one is Friday of this week. There's going to be 6 total. So I have Friday, there's one, and then Wednesday, Friday, then we have our midterm. And then this is the holiday, so I won't have a quiz the day after the holiday. So 6 total. You can figure each quiz is 5% of your grade, so you don't really want to blow off a quiz, although it is survivable if you do. Okay. So that's the gist of it. There's the grading. The book that we're using is UCI has printed up a special version. You probably found it by now. Mine's a little worn. So there's a larger book here, but we've just printed up a few chapters, 7 through 13 here in this book. So you're entitled to purchase the whole book if you want to find it online or something, but all you need is the one that's provided in the bookstore, printed up by UCI. So that's what you need. And then all the homework questions are, let's see, let's go back. This is the syllabus. I didn't want to do that. I'll help you find it here. So you can go to Triple E. You don't even have to log in. You can just go to class websites, and then class websites, math. And then here this is, you got to change the term here. There it is, Math for Economists. Okay, and then there's all the homework. So as soon as I start talking about the book, I'm forced to talk about why this class exists in the first place. Why is there this Math for Economists class? Well, the economists at UCI, they've been complaining over the years that when they want to teach economics, the students are hampered by their math knowledge. And so they've asked that we provide a course that supplements your math knowledge so that they don't have to spend their time teaching you math. They want to teach you economics. So it's kind of understandable that there's this common ground that you need to have in order to understand economics, but if you don't have that, then they need to spend their time teaching you that first, and so they don't end up being able to teach what they want to teach. So they've asked us to teach this course. We've been doing it for a lot of years. So the first thing I want to communicate to you is this is a math class. I'm in the math department. The class is designed by the math department. We have to get approval from the econ department, so we want to make sure that we cover certain topics that they think are important. But the gist of the class is this is a math class, not an econ class. However, it's got economists in the title. We've got this book. This is Mathematics for Economics. So it's going to have a little bit of economics in it. You can't really just do the pure math. But the idea is that you want to get good at the math so that when you go to do the economics, it's solid in your mind. So why is that important? Well, what do economists do? Let's just think about it. I mean, all of you, I have to assume, is anybody here not an econ major? Most people are that take this class. Sometimes I get people outside the department. But so you guys are all potentially budding economists, right? You're getting ready to become economists. Now, you might not be a professional economist. You may just major in economics and then move on and do something else, which is probably pretty normal. But the design of the university is this is a center of knowledge, right? This is where research happens. This is where people come to share ideas and further the knowledge of the human race. That's the idea of a university. So what we're here to do is we're here to prepare people to do that, which means we have to design the classes to prepare people to go to graduate school. Now, you may not be going to graduate school. In fact, most of you aren't. That's the problem here, is that it's designed for people to go to graduate school. That's what the degree at a UC is for. So then when you're finished here, you're capable of then applying to graduate school and then being successful there. That's the design. So you have to ask yourself what it is that you're here for. If you're here for that, then great. You're in the right place. If you're not here for that, there's some hybrid of that. Maybe you want the knowledge, but maybe you're just here to get a degree. This is just a stepping stone for something else. So you need to identify for yourself, what is it you're doing here? Not just in this class, but at the university as a whole. Once you identify what you're doing here, then you can have a plan of attack. So if your goal is to go to graduate school, then you should be trying to learn everything you possibly can. You should get really into it. You should be so curious and so motivated to learn every possible detail you can, because that's what's going to be required of you when you get to graduate school. So you might as well just start that mentality now. If that's not your goal, and your goal is to get a certain grade, for the class and move on. This is just a stepping stone. This is just one piece in the degree. You got to get past this to get to the next class. If that's your attitude, that's fine. That's the normal attitude. I mean, probably 80-90% of you have that, so I'm not picking on that. I'm just saying that once you identify that, then you have a different approach, right? What you want to do is you want to get the information that's outside of your head into your head so that you can take exams, you can pass them successfully. Hopefully you can retain the information, but more importantly, you can still preserve your time for other things, because it's not your main goal to learn all this stuff and be totally dedicated to it. So this is a math class, and we're going to be studying matrices. So I thought it's appropriate that I pull up a clip from the movie The Matrix, because after all, we're going to be learning math, and we have to take a second to first figure out, how do you learn that? Let's say you are that person that's just trying to get through this, it's a stepping stone. Then the question is, how do you get the information that's outside of your head into your head in the most efficient way? So we're gonna watch a little clip here, The Matrix. I'll write a helicopter here. Let's see if I just get it with that. There we go. And I hope I have volume. Sometimes I don't have volume in these courses, in these classrooms. Can you guys all see this? Oh, is it not coming up? I think it was just about to work. Probably going to give us an ad. Can you slow that thing?
Not yet.
Operator.
Tank, I need a pilot program for B-212 helicopter. Hurry. Let's go.
Okay, that's all I wanted you to see. So you see that download? Isn't that what we're doing here? Wouldn't you like to be able to walk into the exam and say, I need the Math 4 midterm download? Okay, ready to go. Wouldn't that be nice? So that's the goal. Obviously, we're not quite there yet, but that's the goal still. So what I want to do, first of all, is just change your thinking. My thinking's been changed. When I saw that movie, it kind of triggered something for me. As a teacher, I was thinking, when I saw that, you know what, I'm not really teaching and the students aren't really learning. I want to put that in a 21st century mindset. What I'm really doing is, I'm a biological computer. This is my hard drive or my operating system. And what I do is, I've got this training, they've programmed me, and I can take my eyes and I can scan these books, and then it goes into my computer, and I have certain training, certain software that's been uploaded. And then what I do is I kind of mix it around, and then I download it for you guys. It comes flying out my mouth, right, as vibrations, sound vibrations. And it comes out of my hand onto the board. I wiggle my hand in certain configurations, and chalk goes onto the board, and then the light from that goes into the room, and then it goes into your eyes. And you download the information that I upload from that experience. So we're all just biological computers, and there's information that's outside of our hard drive that we want to get in there. So now when you start thinking of it in those terms, what's the most important issue when it comes to downloading? Is it quality of understanding, or what is the issue? What's the main issue with downloading? What makes one download better than another? Speed. So now you might think of learning as, okay, you're downloading information, but now it's all about speed. How do you do it quickly? How do you get this done? How do I get the information in there in as little effort as possible so that I can go off and do these other things that I like doing? And I don't have to spend all my time studying. So for those people who are not trying to get every little nook and cranny and learn every little detail about every little thing here at the school and trying to memorize the library, now you look at it in terms of just how quickly can I get this information into my head? Now everyone's going to be different. For instance, someone might like to download at midnight, and someone might like to download at 6 a.m. Someone might like to download at the library. Someone might like to download at a cafe. Right? Everyone's going to be individual, but you need to decide what's the most efficient way for you to download. So that's general. That has nothing to do with this course, or it's just, if you want knowledge that's outside your head, figure out how to get it inside your head. So what are the ways? What are the entry points? Well, your eyes, right? You look at stuff, you're downloading it, you listen to stuff, and also your tactile senses. Those are the three main. Of course, you can smell stuff, but it's not going to help you with studying. And you can certainly try to eat the paper. That's not going to help either. So the main thing are those three senses: the sight, the sound, and the tactile sense. So try to use all three. Have you ever said things out loud when you study? Have you ever just copied stuff out of a book or copied your notes? That's all the download. So you'll have to figure that out for yourself. I just want to just put that idea out there so then you can take it and run with it if you feel motivated to. Okay, so that's just in general. Now, specifically, how do you do that for math? Because you're going to be doing that a lot in math in this class. So I need to spend a little bit of time talking about how do you download math in particular. What I've found is, so here's the thing. Let's say I do a problem on the board for you. And then you kind of look at it and you go, okay, I get the gist a little bit. Now I'm going to go try the homework problems. But you can't even do the problem that you watched me do. Wouldn't that be the better place to start? So when you're downloading math information, what you always want to do is start with something that's ridiculously simple and then just start adding on to it and just build it and build it and build it until you're now doing something that's really complicated, but you view it as having been built up from something simple. So that's always the way you want to do it. A simple way to get this job done is if you have a problem, let's say I do a problem in lecture and you copy it down, you have the complete solution. Take a clean piece of paper, and until you can go from the beginning to the end without looking at the solution, then you're not ready to move on. That's as simple as I can make it. Now, if at the end you can't do the problems, then ask yourself, did you do that? And the answer will be no. Okay? That's how you learn math. Okay? I want to learn how to do this problem. There it is. There's the solution. Clean piece of paper. Oh, I got stuck. Oh, what was that step? Oh, yeah, that was that step. Throw the piece of paper away. Clean piece of paper, start at the beginning again. Until you can go from the beginning to the end without looking at the solution, you're not ready to move on. Okay, there's your formula for how you learn math. So now what I'm going to do is I'm going to upload a lot of problems onto the board. You're going to write them down. Your first time learning that material will be when you copy it down in class, but you can't expect much out of that. Just let it happen, let it wash over you. Then you go home and you try to reproduce those things. Now, you might be much more skilled at somebody else than at reading it. Maybe you can just read them. Okay? But I do recommend writing them out. So that's the goal. You want to download the information as efficiently as possible. And I gave you the secret for math. You can do that in other subjects too, but I'm more comfortable talking about math than other subjects. Okay, now, what about economists? Why do they even need math? Let's convince ourselves that that's important, that the economists really do need math. Before I do that, let me figure out how to get this screen up. All right. So an economist is somebody that is fascinated by the economy. Okay, that's a generalization, but I think it's pretty much true. But what does that mean to be fascinated with the economy? The economy is a vast subject. You could be fascinated in the history of an economy, or you could be fascinated by the social implications of an economy, or you could be fascinated by the monetary policy of different countries, or whatever it is. There's all these different aspects. And what happens is, as an economist, you look out into the world, you find something that you're fascinated with, and you start to study it, and quickly what you realize is that you can't understand it unless you put it in mathematical terms. Then you can start to understand it. So let's take an example here. In 1964, and then in 1965, something happened in our economy, which I think is fascinating. So as an amateur economist, I look out into the world, and maybe I study a little history. I kind of like history. And I see what happened here is we have a silver dollar here and a silver dollar here. Or that's not a silver dollar. So here it was silver. And here it was not silver. Just one day you just woke up and the coin that was minted wasn't silver, and the year before it was minted in silver. But in 1965, the coins were sitting there together in the economy and they were equal. So you could say in 1965 we had the situation where the new was equal to the old. So this gives you an opportunity to see what's going on in the economy in the last 40 years. Well, okay, let's fast forward. Now let's check out today. If I take those same two silver dollars, if I happen to keep them, now this one is worth, I have to spend $20 to get them. So now in the new situation, the old silver dollar takes 20 of the new. So we have an opportunity here to do a little math to understand what's going on in the economy, right? Let's do division. So the new money is equal to 1/20th of the old money. And then we'll do some more advanced math. I can replace that with a decimal version. So then what's important? What's important is the economist looks into the world, sees something interesting, tries to model it using some mathematics, and then there's a really important thing that has to happen. You have to be able to make a prediction from it. It doesn't do you any good. We already know what happened in the past. We're living in the present. So if I don't get any information about the future, it's not really useful. So let's check it out. So our new money today, has lost 95% of its value. So where do you think things are headed? What's the prediction? Is it going to go back to this? Or is it going to go to zero? I'll let you make your own conclusions. But you see, that's how you use math to understand what's going on. Let's do another one. Maybe you've heard of the money multiplier. The money multiplier. So what is the money multiplier? It's the amount of money that gets created after you just create $1. It multiplies. So the idea is if the Federal Reserve makes $1, you end up with $10 in the economy. How does that work? So let's look at that. So so you create $1 $1. We're just going to wipe the whole economy clean. And then, by the way, that's what economists do, is they simplify things, because the real economy is very complex. There's all these things going on. So if you want to understand one aspect, usually what you do is you just simplify things and then try to understand it in the simplest case. So let's wipe the whole economy clean. Let's have $1. Okay, they just printed the very first dollar. Now the rules that we're going to play by is the fractional reserve banking. So the bank must keep 10% of deposits. That's the rule. Must keep 10% of the deposits. So that means they can lend. Right? That's the implication. Well, that's doing high math, right? If they have to keep 10% of the deposits, well, then they get to lend 90%. So let's take a look at all the loans. Let's take a look at all the loans. So the very first, now this is sort of a side note, but the most amazing thing is this original dollar that gets created, that gets lent. That's impressive, right? So they create a dollar and then they lend it either to the government or to a bank, and then there's interest charged on it. So to say it's 2% interest at the end of the year, someone owes them $1.02, but there's only $1 in the economy. So that's sort of a side issue that's kind of important. But let's just take a look at the loan. So the very first loan is $1, and that goes into the bank from the Federal Reserve. And then the bank has to keep 10%, right? They must keep 10%. So then they have 90 cents available to lend out, right? Now what happens is you lend that out to somebody and it goes into the economy and it moves around and people buy stuff with it, but eventually someone's going to take it and put it back in the bank, right? At some point it's going to go back and someone's going to say, well, I'm going to put some of this back in the bank. And it might not be all at once, but eventually the 90 cents or a portion of it, a good portion of it, will be back in the banking system. So then the next loan will be 90% of that 90 cents that went back in. And that's 0.9 squared. So now that's the amount that they've just now lent out to people. So now it's floating around the economy, but then it ends up back in the bank sometime, and they can then loan, guess what, 90% of that. So the next loan is 0.9 cubed. It's 0.9 of this, because it ends up back deposited into the bank. And you can just keep going. So let's do a little math here. I want to know what the total loans. Well, it's 1 plus 0.9 plus 0.9 squared. Then the next one is 0.9 cubed. And it just keeps going. And then so how do we figure this out? This is a prerequisite to this class. In calculus, you learn about a geometric series. The sum of r to the n is equal to 1 over 1 minus r, as long as r is less than 1. So that's this. If I write this out, this is 1 plus r squared plus r cubed plus dot dot dot. So that's what we have over here. R is 0.9. So this is the same as 0.9 to the n, which is the same as 9 over 10. And now we're in that situation. So I can use the formula. It's 1 over 1 minus 9/10. And that's equal to 10. So we create $1 and it goes out into the circulation, and out of that banks can create $10 in loans. So that's nice. But you see how if you didn't understand the math, then what ends up happening? So what you learn in economics is they just give you a formula. They say the money multiplier is 1 over F, where F is the fractional reserve rate. So if I just gave you that formula at the beginning, I would say, well, they have to keep 10% of the deposits, so that would be 1 over 1/10. So that's 10. So that's an easier way to compute it. But you see, you don't, in understanding the math, it's revealed exactly what's going on. Here you just memorize it and you don't really question it. You just go, okay, yeah, the money multiplier, I can get it right on a test. But what is it? Why is there a money multiplier? Okay, that's why. That's why. But you see, that's why math is useful for studying economics. Now, it's not that you really have to be convinced of that. You've had enough economics classes. You probably know that math is useful. But you see how you can get a depth of understanding rather than memorizing formulas? So let's talk about what the goals for this class are. The goals for this class. We're going to survey certain math topics that have been traditionally used in economics. So there's a list of those things. That's probably not one of them. I mean, it would be eventually if you studied a math of finance class or something like that. You'll eventually study that stuff. But for this class, we're going to, the first thing is we're going to have a survey of two different branches of mathematics. One, linear algebra. And not just calculus, I want to say calculus, but it's more than that. It's multivariable. Multivariable calculus. So we'll be going through different topics, and this is the first part of the course. This is up through midterm 1. And this is the second half of the course. Then the other thing that I think you'd like to get out of a class like this is mathematical maturity. So what do I mean by that? I mean that you need to, at some point you need to stop being intimidated by notation. So we need to practice that. Okay, if you don't have a course like this where we take simple settings and work on notation, then you get thrown into economics courses and they have all kinds of notation, and then you get bogged down on that. You get stuck thinking about the notation. So you need to just get used to it. Okay, so that means notation, abstraction, thinking about things abstractly, generalization, and maybe some proofwriting. So that's just all mathematical maturity. So you get ready. And then the third thing that I'd like for you guys to get out of this class is intuition. So let's just do a little experiment here. Let's practice on your biological computers. Let's see how it works a little bit, okay? So I'd like for you guys to all imagine the contents of your refrigerator door. Okay, and now watch what happened when I said that. Did you... What popped into your mind? So somewhere there's a file in your brain, right? When I say refrigerator door, there's a file, and maybe you retrieve that file and you can see your refrigerator door. You can kind of scan over it. Maybe the resolution isn't so good that you could sit there and look at everything, but different people have different abilities on that. But still, I think probably just the general picture or the feeling of your door just showed up in your mind, and you could just kind of go through it, right? What's there? Very few of you, if any, had a piece of paper pop into your mind with a list of things. So what that shows you is that your mind prefers pictures. It stores details in pictures, right? If you're going to retrieve something quickly, your mind can do it really quickly if it's a picture. It can move it around, it can do amazing things. But if I said, recite all the contents of your refrigerator door, that would take you a while. You'd sit there and you'd say the different things, okay? So what I'm revealing to you is that your mind really relies on the visual. It really likes the visual because it's instantaneous. So when I say that that we want to develop our intuition, what we want to have is when I put mathematical symbols on the board, that when you look at it, pictures pop into your head. So that then you can move around in your head on the pictures while you're doing the stuff in the algebra or whatever it is we're working on, the calculus. So that's the third thing. Okay? We're going to do survey of these subjects. Along the way, we're going to work on our notation, abstraction, generalization, a little bit of proofreading. Not a lot. I mean, you'll see. That's not that big a deal, but it sounds intimidating. And then the other thing I think is probably even more important is that you have some pictures in your mind for these mathematical concepts. All right. Does anybody have any questions for me? Okay, we'll start with section 7.1 in the book. This is solving systems of equations. The first thing that we need to do is to remind you that you've already solved systems of equations in your life. You did it in algebra, even before geometry, where you had, two lines and you see where the intersection of two lines is. So you've already done this, but let me add a word here because I'm going to focus on vocabulary here. This is important. Linear equations. Okay, so the first thing, we've got some vocabulary here, and I'll challenge you that when you don't understand something in math, it's usually that you don't understand the vocabulary. That's almost always the case. So you really want to put a little time into understanding what the words mean so that when the word pops up in front of you, you get something that is conjured in your mind that you can relate to. Okay, so first of all, a linear equation. Let's just understand that term. It comes up all the time. You may already be comfortable with it, but let's make sure everybody's on board. Okay, so a linear equation. Well, it's got to have an equal sign. That's what the word equation. And then linear, in your mind, it should trigger line. But line is limited because that's only when you have two variables or one variable. When you start to have more variables, you still need to have the concept of linear, but it's not going to be a line anymore, not always anyway. So a linear equation, okay, well, we can have any number of variables. That's not restricted. But the variables can only have powers of 1. That's it. That's why it's the most basic function. Okay? Even constant functions are still linear. So powers of 1. And then the coefficients can be any real number. Any real number. That was smooth. This is not smooth. That's going to be a little bit of a problem. All right, let's go through it. So we can have n variables, so let's just go through, different levels of that. So if I have one variable, then that's like x equals 2 or y equals 3. And so those are linear. Right? Here's x equals 2. Here's y equals 3. So those are linear. So even if you just have one variable, see the variable only has a power of 1, then you get a line. If I have two variables, this is still your familiar setting here. If I have two variables, 2x plus y equals 1. This is specific here. This is an example of something specific. So then how do you write down, let's write down every two variable linear equation in the universe. We have a finite life. There's infinitely many of them, but let's get it all done. All right, I can do that. See, the thing that defines this is just these numbers in front, these coefficients. So if I want to write them all down in the universe, this is what I mean by generalization. I want to write them all down at one time. Well, then that's ax plus by equals c. Right? And I don't specify what a, b, and c are, so that's everything in the universe here. This is general. If I write down three variables, well, it starts to get a little repetitive here, but I have to have three variables, so I'm going to say x, y, and z. And then to make it specific, I have to put some real numbers as coefficients in front, so it doesn't matter. You can have 2, 3, and -1. And then I have to have it equal something, otherwise it's not an equation. Okay, so now how should we visualize this? What happens when we have three variables? Here you can visualize that one is, it's got a slope of -2 and it's got a y-intercept of 1. So, there I can visualize what that picture is because you guys have the training, right? You had the software downloaded when you were younger. So you can look at that with your eyes and conjure up a picture if you practice it. But what do you do about this? What about the third variable? Okay, well, it's still linear because it satisfies this condition. It only has powers of 1, but this isn't going to be a line. So this is where we depart from linear means line. All right, well, what I want you to do is think of each variable as being a dimension. Okay, so I have two variables. I have two dimensions. I have x and y. Those are my two dimensions. Now I have three variables. Now I have x, y, and z. And the way to do this in your mind is if I'm going to add a dimension, then just grab this and just pull it out from the wall. Can you do that in your mind? Just take that and just pull it out from the wall. So what I get is a plane. So a plane is the linear equation in 3 dimensions. And that's as far as you can go when it comes to seeing it in your mind, because when we go to 4 variables, then it's in 4 dimensions and you can't see that because we live in 3 dimensions. Okay, for a second we just want to go one step further. This is the standard stuff. 1 variable, 2 variables, 3 variables. But we can do more, and the reason I want to mention more is because this now gets into the notation. What happens when we start having, let's say we have 10 variables, or let's say we have 27 variables. Well, if we have 26 letters in the alphabet, then we'd run out of letters, right? So this wouldn't be an appropriate way of labeling variables if I had 27 variables. So what happens is once you get beyond 3, you usually stick to subscripts. So if I have 5 variables, let's skip over 4. Let's just go straight to 5 variables. Then you wouldn't write it, A, B, C, D, E, F, or something like that. What we're going to do, and this is more appropriate for economists, is you label the variables with subscripts like good 1, it's x sub 1, and good 2 is x sub 2, and good 3. So that's what you want to think of in your mind when we're doing this, is some of the economics models that you've seen. So for 5 variables, I might have something like x1 minus x2 plus 2x3 minus 4x4 plus x5 equals 7. So that's a perfectly good linear equation in 5 variables. You don't really have any hope of seeing that. So at some point, the visualization stuff breaks down and you have to rely on your algebra. So we're going to have to work on that quite a bit, on the algebra part. So if I have 5 variables, that's what it looks like. This is linear. And then how about, let's do even more of this notation and generalization. Let's write down every linear equation in the universe. So I can't say that it has any specific number of variables. Let's say it has n variables. All right, well then how do I do that? I got to have x1, and I got to have x2, and I got to have xn. But then I could have, see, over here, when I wanted to write down the general one, I put in letters here to indicate that it could be any real number. Well, again, I'm going to run out of alphabet letters, so I don't want to use A, B, and C. What I'm going to do is I'm going to label the coefficients also with indices. So the coefficient that goes in front of this guy is A1. And then this is A2. And then it goes all the way down. And then I have AN, XN. And then it's got to equal something, so we'll say it equals B. So this is all the linear equations in the universe, because if I want 1,000,000 variables, then I'll just put 1,000,000 here and I'll have 1,000,000 of them going out. If I want 1,000,000,000, that's fine. If I want 2, I'll just stop right here. And notice if I stop with 2, that looks just like this one, except you have x1 and x2 instead of x and y. Okay, so that's linear. That's just handling that vocabulary, linear equations. So now what we're going to be interested in is solving systems of linear equations. So now you have to wonder what that word system is doing there. Why is there a system? So let's take a look at that. Let's have some nonlinear stuff too to compare. So this is nonlinear. Okay, so root x plus y equals 3. So I have a power that's not 1, so that's just nonlinear. Okay, and you want to just think it's got some curve to it. As soon as it's nonlinear, it's got some curve. Can you picture that in your mind? How strong is your computer? How updated is it? Can you look at the symbolism on that page with your eyes and have something pop into your head? Maybe, maybe not. That's just a little test for yourself. We'll work on that. Do the same with this. Nonlinear. Okay? Nonlinear because the power is not 1. It's -1 in this case, not 1. So these are nonlinear. And then something like x squared plus y squared equals 4. Can you picture that? Can you picture what this is? This is a circle. And then this guy here, root x. Let's just go over off to the side here. Y equals root x. Why is root x important in economics? Well, you can't answer that question unless you can see it in your head. And even if you can see it in your head, you might not be able to answer the question. But let's just see it. Okay, what does it look like? Where have you ever seen that shape in economics? There's a law. What's a law that's got that shape?
Diminishing return?
The law of diminishing returns, right? So when you're modeling, when an economist looks out into the real world and says, oh, that's interesting, I want to model what I see, when they notice this law of diminishing returns and they want to incorporate it into their mathematical model, they're going to use functions with fractional powers. Because it's not going to be linear. Right? The law of diminishing returns is not a linear function. It's a fractional power. We'll get more into that later. How about 1 over x? Let's take, because these are fundamental graphs for economists. So why? This is 1 over x. Now you have the negative part here too. I kind of draw it lightly because in math that's the true graph, but in economics you don't really deal with negative amount of goods, right? Or negative production, stuff like that. So negative labor, right? What does it mean to have negative 3 workers? So in economic models everything's positive. But anyway, where have you ever seen that shape in an economics class? Comes up all the time. I mean, I don't know what level you guys are at, but
Complements?
huh?
Complements?
Yeah. Okay, so that comes in utility functions, right? Complements and substitutions. So this is an indifference curve. Indifference curve. Okay, maybe you know that term or you don't. So that's why these graphs, so when you put an x on the bottom, it creates this shape, and that models something that they see in the real world. So they use these functions. So if you're not familiar with them, then when you go to study with them, you get bogged down in trying to deal with the math instead of learning the economics. So those are nonlinear equations. This one's a circle, radius 2. I pick those because they keep coming up later in the class. We might as well get our first introduction to them. Okay, now let's go back to that word system. So the system part of that statement over there, this just means I have multiple linear equations. Multiple linear equations. So now we're going to start stacking them. Okay, we've spent a lot of time just figuring out what a linear equation is. Now we're going to stack them. We're going to have a bunch of them. So what we need to do is we need to go back to when you first saw that and practice that and get comfortable with it. Okay, so here's the possibilities. Well, one is we could have a unique solution. You could have no solution. Or you could have infinitely many. When we start getting into the category of 3 variables or 5 variables, then figuring out each one of these situations is increasingly complicated the more variables we have. So what we want to do is go back to a really familiar situation where we had all these things happen, study that, and then build on that. That's the goal. We'll start with 2 variables. So the first situation is the most common, and this one also, when you're thinking about these systems of linear equations, what should you be thinking about in terms of economics? Where have you seen systems of linear equations? What's the setting that you should be keeping in the back of your mind when we're doing this? Supply and demand. Equilibrium, that's a more general way of saying it. Just equilibria. When you're finding equilibria then you're often solving systems of linear equations. So supply equals demand for different goods, supply equals demand, that gets you a system of equations, and you find the one point where the economy is in equilibrium. Okay, so for two variables, the unique solution, that should be familiar to you, right? For supply and demand, that's the supply and demand equilibrium. So this is the unique solution. And so again, when you read unique solution, what does that conjure up in your mind? Does that mean anything to you, or is that just words? So you have to be really careful that when you're reading math terms, that you don't just glaze over it. You don't just say, oh yeah, unique solution. What does that mean? Why do we use this word unique? What's going on? What's the solution? Okay, let's translate that. That means you have one point that satisfies both equations. That's what a unique solution is. Now, I'm not telling you anything you don't already know or you haven't seen before. I'm just trying to refresh your memory and then maybe conjure up some new thoughts about it. So that's the most common. The second one is when you have no solution. Let's put this up a little higher. What does it look like, first of all? If I tell you have a linear system and there's no solution, can you conjure up the image in your mind? Well, the image is parallel lines. That's no solution because there isn't, what's a solution? It's a point that satisfies both equations. There is no point that satisfies both equations, so that's no solution. Here we have parallel lines. And then the third case, this is 2 here. Here, I'll bring out my trusty, I guess I can use this here. Okay, so if you have infinite, the third one there is infinitely many solutions. So if I have one line, I have two variables, and then I have a second line that's exactly the same. That's probably not a good, let's use this chalk here. So I have two lines on the same, that didn't work either. So this is infinitely many. And that means they're the same line. Okay. Now these are degenerate cases, but what we're going to want to do is, see now for each of these, let's add a variable. This is our first opportunity to practice with more variables. So for each of these, pull these out of the wall. Add the dimension. Okay, so here, if I pull that out, I have two planes intersecting. What happens to that point? If I pull this out of the wall, what happens to that point? It becomes a whole line, right? So if I have two planes intersecting, then you'll get a line as the solution, and that'd be infinitely many solutions. So these are the simple cases. If I pull this out, then it's like having two planes stacked on each other, right? They don't intersect. And then here, well, if I pull those out, I just get two planes sitting on top of each other. Okay, so let's have some examples. See, what we need to do here is, what we've been working on is intuition. I don't have that up there anymore. But this is just intuition. Now we need to go and work on the algebra. What are the equations that give you these settings? So for the first one, if I have x plus y equals 2, x minus y equals 0, then we'll just do these quickly. I'm not going to spend too much time on this. So there's a system of equations, a system of linear equations in two variables, and then the solution is right there at that one point. That's a unique solution. And then what would it look like if I have parallel lines? Well, then I have x plus y equals 2. So what has to happen if I have parallel lines, these coefficients are the same because those are what define the slope. So I'm going to have x plus y. But now if I put a 2 here, they'll be the same. And if I just put something different, like a 4, then they're parallel because all that did was change the y-intercept. So I have 1 that has a slope of -1 passing through 2, and 1 with a slope of -1 passing through 4. And then what does it look like if I have the exact same line? Then, well, the simple thing is that I would just have a 2 there, but that's kind of silly to write because they're exactly the same. So really in practice, if you had 2 of the same lines and you couldn't identify it right at the beginning, it'd be because it was disguised a little bit. So what does the disguise look like? Something like this. So at first glance, you might think you have 2 different equations there, but when you realize that if you just divided this one by 2, you'd have the original one. So this gives you the same line. So this has infinitely many, this has no solutions. And this one has a unique solution. Well, the title of this was Solving Systems of Equations. And what I did was, first we said, okay, what's a linear equation? Spent a little time on that. Then we said, okay, what's a system of linear equations? Now we spent a little time on that, just in 2 variables. So now we need to start solving them. The idea is to find this solution. If you're trying to solve them and you get those cases, that's kind of a degenerate situation. So those don't come up as often. But when you get to more variables, they start to. So that's why we need to mention them. Okay, the first one is just reminding you that when you learned this when you were younger, the first thing they did was they taught you how to graph lines. Then they gave you a couple of lines and they say graph both of them and then find that point of intersection. So we'll have a simple example just to remind you that you could still do this. But I also want to do it to illustrate that it's not that satisfying and it's not very effective all the time. Okay, so if I were to graph this, this line here is the same as x equals 2. So I can graph that vertical line. That's the first one. And then this is y equals x plus 1. So it's got a y-intercept of 1 and a slope of 1. And I would discover that that's the point of intersection. That's the point 2, 3. That's the unique solution. Now it's not hard to see that if I added a variable here and we just pull this out from the wall, then you're not going to be able to draw that and figure out what the intersection is. In fact, there are going to be infinitely many solutions, so it's not going to be, this isn't an effective way to solve systems when you get to higher levels. So this is nice and everything for your high school algebra course, but we're going to need something more sophisticated to get the job done. If you recall, when you learned this when you were younger, one of the methods that you learned was the substitution method. So let's have an example of that to remind you. So here's a system of linear equations. And the goal is to find the point xy that satisfies both simultaneously. In your mind, when you see this, you don't even have to have an accurate picture. You just, in your mind, you just go, okay, I'm looking for that point. See, that's how you develop your intuition. When I see this symbolism, I get a picture like that in my mind. That's what I'm looking for. Okay, so the substitution method would be to solve for one of the variables and then substitute, hence the name. So let's do that here. If I solve for x here, I have x equals 3y minus 18. And then what we do is we take this version of x and we substitute it right there. So now I have 1/3 x is written as 3y minus 18 minus 2y equals negative 11. So if I multiply all that out, I get y minus 6 minus 2y equals negative 11, or y equals 5. And then once I have y equals 5, I can go now back substitute and find out what x is. So y equals 5 and x equals 3y minus 18. That implies that x is equal to 3 times 5 minus 18, or negative 3. So my unique solution is negative 3, 5. Okay, simple substitution method with two variables. It's kind of unfortunate I have to deal with these boards. I guess I'll get better at it. Okay, the next method that you may remember learning was the elimination method. So the word elimination corresponds to the process of eliminating a variable. Remember, if you can eliminate a variable, then you only have one left, and then you can solve for it. So that's the idea. So let's have an example of that. So the idea here is, this is how you were trained, hopefully, that you look at that x and you say, you know, I could eliminate that x if I wanted to. How would I do that? I would multiply this by negative 4, right? If I multiplied both sides by negative 4, then would I, as a result, I would end up with a negative 8x here. I'd end up with a bunch of other stuff. It's going to get modified, but ultimately I could add the equations, and then the x's would go away, and I just have 1 with a y, and I can solve for y. Now I want to have you think of it this way. When you're adding this equation to this one, think of it as incorporating this information into that equation. So first of all, let me just write down what I have here. I have negative 8x plus 12y equals negative 20. And then the equation here, 8x plus 7y equals 1. So when I'm doing this adding, I know we're just going to do the adding and it's just about arithmetic, but intuitively what you're doing is you're taking the information from this equation and you're incorporating it into the equation, the second equation. So when I add those, I've got both lines in one equation. So I get 19y equals negative 19, so y equals negative 1, Okay, that's how we got y, and then what we do is we back substitute. So now we're doing a combination of elimination. Then I take this value here and I substitute it back in and find out what x is. So y equals -1, and the information 8x plus 7y equals 1. That gives me 8x minus 7 equals 1, so 8x equals 8, so x equals 1. So we have our solution is 1, -1. That one works. Okay, now let's just quickly go and look at those two degenerate cases and see what those look like algebraically. The degenerate cases. Okay, the first one was parallel lines. We want to be able to look at the equations and identify it as parallel lines without having to graph it. That's why I'm doing this. So the second case would be if I had parallel lines. So the typical equation would be 2x plus 3y equals 4, and then 6x plus 9y equals 11. So I can look at that and immediately know that there's no solution and that they're parallel lines. So how can I do that? A couple of things. When I see that this guy is the same multiple of so 6 is 3 times 2 and 9 is 3 times 3. So when these are the same multiple, then I know there's the same slope. So same slope means parallel lines, unless they happen to be the exact same line. But the fact that these are not a multiple of 3 means that we're going to have parallel lines instead of the same line. If this was a 12 here, then they'd be exactly the same line. So let me just write that down here. Here we have multiple of 3, and here they're not. So look what happens when you go to solve it. This is the important part, is that when you go to solve this, I could multiply this by -3, right? I get -6x. Let me not put a line there. Let's go over to the side and do this. So I'm going to do -3 times 2x plus 3y equals -3 times 4. Just multiplying both equations by -3, both sides of the equation by -3, and then I have -6x minus 9y equals -12, and then I'll put that bottom equation beneath that, and then add, so I get 0 equals -1. See, so now you know it's nonsense, so that's no solution. So algebraically, when you get no solution, you should get some kind of nonsense when you're trying to solve it. You should get, 5 equals 7 or something like that. Something that doesn't make any sense. That's what should happen. Okay, and then let's see what happens with the same line. So if we have 2x plus 3y equals 4, and then 6x plus 9y equals 12, here the multiples are consistent. I've multiplied by 3 on this side, and the same multiple is over here. So that's going to create the same line. I can reproduce the top one by multiplying by -3. Same as over here. Just making a match so I can eliminate variables. That gives me -6x minus 9y equals -12. And then the other equation, 6x plus 9y equals 12. And so now if we add those, we get something different. The algebra gives us 0 equals 0. So you compare that to the 0 equals -1, so that's the distinction. When you get something like this is not nonsense. What this is just you didn't get to find out what the variables are, which means that there are infinitely many solutions for this. So this is infinitely. So every point on this line is a solution. Okay, so this is a natural point to just take a pause. But what we've done is I just did all your high school algebra stuff again. Okay, so hopefully you're able to follow it. I mean, when it comes to systems of linear equations. So now we're going to start building on that. So like I said at the beginning, the way we want to learn this, the way we want to download this information is to start with something you're really comfortable with. Remind yourself of it, get thinking about it again, and then we'll start adding to that and start making it more complicated. That's the design, that's the style that I'm going to try to incorporate into this class. Try this. Okay, so section 7.2 is about now we go to more variables, and what happens is there's two things we consider. There's the number of equations and the number of variables. So when you did it in high school, you just stuck to the simple situation where you had 2 variables and 2 equations. You didn't really mix it up too much. So even with this, we're going to build it up slowly. Let's start with a standard example, just to kind of motivate us. So we're going to have 3 variables and 3 equations. But as I write that, imagine in your mind we could have all the different combinations. We could have 5 variables and 3 equations, or I could have 3 variables and 2 equations, or 5 equations and 2 variables. We can have all the different combinations. It's not like you have to have the same number, but we're going to start off that way. Okay, so here's our example. X plus y minus z equals 0. X minus y plus z equals 2. Negative x plus y minus 2z equals negative 5. So where do you start? I mean, this is the problem, is that when you were in 2 variables and 2 equations, you'd seen it before, and you probably already even have a method in your mind that you like best. You maybe do the substitution or the elimination. But here we've got more going on here. We've got 3 equations, we've got 3 variables. So what's the method? How do you start? What do you do? If I ask everybody, you might all come up with something different. So unfortunately, the answer to your question, where do you start, is you have to have some experience. I look at this, I have a lot of experience, so I kind of know what to do. Now all I can do is try to impart that experience to you guys as best I can. But no matter what, it's hard, and even if you can handle this, we can put 4 variables, 5 variables, right? We can keep making it more and more complicated. So let's see what we can do here. Remember, the methods that we learned were substitution and elimination. We could try graphing it, but that's going to be it's going to be hard to do. Okay, so the first thing I'm going to do is I can notice that if I were to add these two equations, I would eliminate two variables. You can just notice that. That's why I say it's largely experience. I look at that and I'm looking for that kind of a thing. I can see that those can be eliminated if I just add these two equations. So if I add these, then what do I get? I get 2x equals 2, which says that x equals 1. So that's good. I already got one of the variables. And then I could take these two equations and add them, noticing that, look, x's will go away and y's will go away, and I'll just have z's, and then I can find out what z is. So if I add these equations, then I get negative z equals negative 3. Which tells me that z equals 3. So doing the elimination method worked pretty well. I got two of the variables. I still need to know what y is, so now I can pick any one of these equations, substitute the x and the z that I know, and find out what y is. So let's take this one here. X is 2, so I have 1 plus y minus z, which is 3, equals 0. So y equals 2. Okay, so here I'm doing x equals 1, and here I'm doing z equals 3. So I'm putting those numbers in there. Now I know what y is. So now my solution, my unique solution, is, let's put it right here, x equals 1, y equals 2, and z equals 3. Now you should be feeling a little uneasy at this point, because you say, okay, well, that was fine, I understood what you did, I saw those steps and everything, but you want to be asking yourself, well, how would I know to do that, or could I have known to do that? And what arises when you start thinking that way is, wait a second, could he make it harder where I couldn't do that method? I mean, this one was pretty convenient, the way the variables just eliminated right away. That was pretty convenient. Maybe I rigged it this way. So what you got to be thinking is, okay, well, what if it's not rigged that way? So we're going to need a method for this. We're not going to be satisfied with just every time we get a system of equations just trying to invent the system or invent the method right there when we're looking at it. We need a method for all this. So we'll eventually get there, but right now we just need to practice a little bit. So let's go to some of these degenerate cases. That's a unique solution. Let's go to one where there's no solution, but we have more equations. So again, more vocabulary, an overdetermined system. Overdetermined, well, when you have a system of linear equations, it's the equations that determine the system. I have a pile of equations sitting there. That's what determines my system. And so if it's overdetermined, that means I have too many equations. So let's just get that settled right now. Overdetermined. And like I said before, when you're trying to understand math vocabulary, I don't know, I didn't say this before, but usually when you don't understand a math concept, it's because you don't understand the vocabulary. So when you focus on the vocabulary in math, think about this thing, that the mathematicians who discovered this stuff, they pulled words that already had definitions from the English language. It's not like they made up words. I mean, they didn't call this the supercalifragilistic system, right? I didn't make up words. That word, they have meaning. So when they attach the words, there's something in there for you to learn, and it usually contributes to your intuition. Okay, so overdetermined, that means I'm going to have more equations than variables. More equations than variables. And then there's an implication to that. What does that mean? So let's start with an example where we have 3 equations. So I got to have more equations than variables, so I better have 3 equations and then either 2 variables or 1. Let's have 2 variables. So what does that look like? Let's just get a picture in our mind. Okay, what would be, if it was 2 variables and they're linear systems, then if I have 2 equations, that's this picture. We've already had that. So there's the solution already. If I have 2 lines, there's already this potential unique solution. So what are the chances that if I add a 3rd line, it passes through that point? Not very good, right? If you just draw a random line, it's just not going to pass through that point. You'd have to be pretty precise and make it happen. So if I just have 3 equations and 2 variables, it's possible I could have a solution, but the most likely scenario is that I have no solution. Okay, so let's take a look at that. Let's see how that plays out algebraically. So if I have x plus y equals 4, and I have negative x plus 3y equals 4, and then I have 2x minus 6y equals 5. Okay, so there's your system. This is an overdetermined system. I got too many equations for it to find a nice solution. Okay, well, what did we do last time? We just tried to eliminate variables. That was convenient. So if I add those 2 equations, I get rid of x. That gives me 4y equals 8. So that tells me that y equals 2. And then if y is 2, I can just go back and plug in and find out what x is. That implies x equals 2, because I put a 2 here, I get x equals 2. So look, I've already solved the system. I didn't even pay attention to the 3rd equation. So that's this phenomenon here. If you have 2 lines, chances are they intersect at a point. And if the 3rd one is going to be part of the solution, it has to pass through there. So now I can just check but 2, 2 doesn't solve this. So if I plug in 2 here, I don't get a solution here. I ran out of space, but I guess I can put it up there. Let's just put it right here. So if I have 2 times 2 minus 6 times 2 equals 5, then I have 4 minus 12 equals 5, so I have negative 8 equals 5. So there's no solution. So even though I got a solution for the first 2, it's got to be a solution for the whole system. And so our conclusion here is that there is no solution. Okay. Now, it's not always the case that overdetermined systems have no solution, but for our practice, you know, if I give you an overdetermined system, chances are it has no solution. Because if I want there to be something that has a solution, I won't give you an overdetermined one. Okay, so that's one of the degenerate cases in a different setting. Now we need to do a similar thing. We need to do the opposite. If we have a word called overdetermined, and that means we have more equations than variables, then we should have a word underdetermined. Or that's how the English language works. If you use the word over as a prefix, then chances are there's a word with under as the prefix that's the opposite. Okay, so that's the next one. This one's a little bit more important, this underdetermined. That one there is, I mean, that's kind of like the parallel, the lines that are, the equations that are the same line. It's just not going to come up that much, even though you should know what it is. So an underdetermined system, this one does come up. I often put this on my exam, so you want to write this down. So an underdetermined system should be the opposite of that. Let's get that straight, the vocabulary. Underdetermined. That means I have fewer equations than variables. So let's have The simplest example of this is one you're already familiar with, except that you just never talked about it in these terms. The familiar example is one equation and two variables. So if I have one equation and two variables, what's that look like? That's negative 2x plus y equals 1. And that's one equation and two variables. So what do we do with this? Well, let's graph it first of all. The graph, it's y equals 2x plus 1, if you like. So there's the graph. So that's what you're trained to do, is if I give you this equation, you're able to graph that. What I'm saying is that every point here is a solution to this system, even though it's just one equation. But what I want to do is I want to practice writing these solutions. So there are infinitely many solutions to this system. Infinitely, every point on this line is a solution. Let me ask you guys, can you see this if I write down here on this part of the board? The room's slow, but what about you guys? Yeah, this doesn't get in the way? Okay. So every point there is a solution. So how are we going to organize this solution? This is good enough, but I want to introduce a new way of organizing it, because when we get to more complicated settings, we're going to need this other way, so we might as well practice it here, where it doesn't hurt so much. Okay, so how do I want to organize this solution? I want to write it down in such a way that it really shows the infinitely many solutions. So what we're going to do is we're going to use what's called a parameter to write our solution. I might need a new classroom. If we're going to film this here, I might need a new classroom. Now that's intimidating, because if you're not really comfortable with math, and when I say, hey, we'll just go ahead and present the solution using a parameter t, go ahead. Well, you don't even know what I'm talking about, right? It's like, that's what I mean by the vocabulary. You don't know what this means, so then it's like you don't even know what to do, right? You're stuck from the beginning. Okay, so what is a parameter? If you want to analyze the language here, para, it's like paralegal, paramedic, parallel. It's a parallel measure. And that doesn't really help you, but anyway, if you want to study the language there, that's what we're doing. So what I want to do is I want to use one letter to organize the x's and the y's. So here's what I do. We're going to set x equal to t, and then I know what y is in terms of t2, because y is 2x plus 1. So then y is equal to 2t plus 1. So my solution can be written like this. This is what I mean by we can present the solution using a parameter. We'll write our solution like this. X equals t and y equals 2t plus 1. And now the solutions are any t and the real numbers. So you give me a t, I'll plug it in there, and I'll find a solution to that one line. You know, that system of one linear equation. So that's writing things in terms of a parameter, which we're going to need now for the next example, but it'll be more complicated. Okay. So now let's have 3 variables, but only 2 equations. So that falls under the underdetermined category because that means I have fewer equations than variables. So x plus y plus z equals 2, and negative x plus 2y plus z equals 3. Okay, so first of all, let's do a little work on intuition here. If I didn't have z here, it was just x plus y, then you just have 2 lines and I'll be looking for the point that the lines intersect. So as soon as I add a z, you want to pull that picture out from the wall, pull the x out from the wall. So then what that gives you is we've got 2 planes intersecting, and they intersect in that line, and that's our goal, is to find that line. We want to find all infinitely many solutions where those 2 planes intersect. So here's the picture here. This is the rather than having the intersection of 2 lines, which is what you're familiar with, now we have the intersection of 2 planes. And we can draw that. We can try to draw it. Okay, so if 2 planes intersect, how do they intersect? They intersect right here in that line. So that's what we want to find. We want to find the equation of that. We want to find, and what we're going to want to do is we're going to want to write it this way, because this is kind of complicated. It's a plane, or it's a line that goes in 3 dimensions. So what we'll want to have is have it all set up so that you tell me a value of t, I can give you a point on that line. That's the purpose of learning to do that parameterization. Okay, so how do we do this? Well, I like that elimination method, right? That's eliminating variables tends to help us make progress. Where's my, there it is. And we also, so we have elimination and we have substitution, right? Those are our 2 methods. So let's try something here. Let's just take this and solve for z. This gives me that z is equal to 2 minus x minus y. So at the very least, I could reduce it down to 2 variables. So z is equal to 2 minus x minus y. Now I want to incorporate that information into the second equation. So let's incorporate it. There it is. So now I have negative x plus 2y plus 2 minus x minus y equals 3. And then we can simplify that. I've got a negative x and a negative x, so I got negative 2x. I've got a 2y and a negative y, so I have plus y. And then I have 2 here, and I can bring that over to the other side. That's 1. See if you believe that. You believe me? Okay. And then this is not how we usually like things. We usually like, y equals 2x plus 1. So at least that's familiar. We just had y equals 2x plus 1. So let's now do this parameterization, which we just practiced on the simple case. Now let's do this in the real live example with 3 variables. Okay, so what I want to do is I want to present the solution. What I've got here is a relationship between x and y, but it doesn't tell me anything about z. You see, this is an incomplete solution. Z is equal to this, and y is equal to this. So we don't have any numbers or anything. So here's where we're going to use that parameterization again. Let's set x equal to t. Okay, and that's always just a starting point. Take one variable, set it equal to t, and now the other one should be in terms of t. Okay, so if I set x equal to t, just like in that previous example, I'll have y equals 2t plus 1. So those 2 are taken care of. And then z is 2 minus x minus y. So z is equal to 2. Well, x is t, so 2 minus t. And then y is 2t plus 1. So now z, what's z equal to? 2 minus 1 is 1. And then I have negative t and negative 2t, like that. So let's write down the complete solution here. So intuitively, I can understand that there's infinitely many, okay? But how do we write it down? Well, we've got it there, but I just want to organize it. So I have x equals t, y equals 2t plus 1, and z equals 1 minus 3t. And this is for t, any real number. So if you give me t equals 1, then 1, 3, negative 2 is a solution. Then we have x equals 1, y equals 3, and z equals 1 minus 3 is negative 2. This is a solution. But we get one of these solutions for any value of t. There's infinitely many of them. So you give me a value of t, I'll give you a solution. And I'll find that solution by this relationship. So that's what you need to learn. This is a great example for you to do what I was telling you. It's probably new to you, so take that example, take a clean piece of paper at home, and reproduce it all the way to the end without looking at it. And when you get stuck, you look at the solution, you go, oh yeah, that's right, I forgot that step. Then crumple up the piece of paper, start over again. So you can go from the beginning to the end without looking at the solution. You are not ready to move on. So that's probably the hardest thing we've done today, is that we built up to it. We put a lot of energy into doing some old stuff so that we could build up to this example here. Okay, so I'll leave it here, and we'll pick up here on Wednesday. I haven't quite finished section 7.2, so I'll pick up there, finish that, and we'll move on to chapter 8. Okay, we'll use the rest of the time. Is the TA here? Yeah, good. He just walked in. And so there's your TA. And then if you guys have any questions, you can come and ask me right now. Okay?